5.3 inverse functions part 1. To review a little bit, you have done inverse functions in Algebra 2 and in pre-calculus. If a function equals x plus 4, let's say, then here are some of the ordered pairs in the function. And sometimes we'll give you functions just with ordered pairs, and sometimes we'll give you the function rule. So let's say we've got 1, 5, 2, 6, 3, 7, 4, 8. Obviously those are points on the line. X plus 4. The inverse function, and we notate that with the f with a little negative 1, it looks like an exponent. That doesn't mean 1 over f of x. I know that if you have like 3, so if you have 3 to the negative 1, that does mean 1 over 3. But f inverse does not mean 1 over f of x. Okay, it's a totally different, same notation, but means something totally different. It means the inverse of f. So if we have x plus 4, then the inverse would be x minus 4. And we'll get into more details about how to find that. I know you learned it in Algebra 2 and pre-calc, but we'll go through it again. But just looking at the ordered pairs, 4, 8 becomes 8, 4. And 3, 7 becomes 7, 3. 2, 6 becomes 6, 2. And 1, 5 is 5, 1. So every ordered pair switches. So the range of f, the y values of the original function, will equal the x values of the inverse function. The domain of inverse of f is equal to the range of f of x. And of course then the domain of f of x is equal to the range of the inverse of x. So theorem 5.6 is the reflexive property of inverse functions. All it means is that if you have an ordered pair, AB in one function, then in the inverse function it will be BA. Do you remember what if and only if means from geometry? If something happens forwards, like if the graph of f contains the point AB, then the graph of the inverse contains the point BA, and backwards it's true also. If the graph of the inverse contains the point BA, then the graph of f contains the point AB. So if and only if means you can read it both ways and it has to be true. So our definition is, a definition of the inverse function, if a function g is the inverse of the function f, then f of g of x, do you remember that means a composite function? If you put g into f, then you work out all the math, it will equal x. And the same thing, if you put f into g, then you work out all the math, it will equal x. So let's do some examples when you're done writing that. So if we're supposed to show that f of x, which is 3 minus 4x, and g of x, which is 3 minus x all over 4, are inverses of each other analytically, we have to use that definition that says that if we put g into f, we're supposed to end up with x. And then vice versa, if we put f into g, we're supposed to end up with x. Do you remember the other note? What?
You have to show both.
Yep. You do have to show both. Remember the notation? It could be this. You've seen this before, right? That means the same thing as g, f of g of x, where you're putting g into f. Alright, so 3 minus 4x is f, and 3 minus x over 4 is g, so I'm going to take that function and put it in to the f function. So f of g of x will equal 3 minus 4, and then instead of x, I'm going to put this function, which is g. So then do math. Mathematically, you have to multiply these two first, so I'm going to cancel those. And then I'll have 3 minus 3, and then distribute the negative, plus x. 3 minus 3 reduces to 0, and so that equals x. So I've shown that f of g of x equals x. That's what an inverse should do. It should undo every operation that was in the original function. Then let's show the other one, g of f of x equals x. So I'm going to put f of x into the g function in place of the letter x. So g of f of x is going to be 3 minus x over 4. And instead of x, I'm going to have 3 minus 4x. Remember the parentheses, because I'm subtracting a quantity, I have to subtract each part. So 3 minus 3 plus 4x. I'm going to distribute, oops. You're going to distribute that negative. So 3 minus 3 is 0. So on the top I just have 4x and then dividing by 4. operations, you end up with x. So that's analytically how to show or verify that two functions are inverses of each other. That will be on your homework. Any questions about how to do that? All right, then. To show graphically, state the domain and range of f and f inverse. What's the domain of f? Let's review how to find domain. Domain is all the possible x values you can put into the f function. Is there anything that you can't put into a function that does 3 minus 4x? No. So the domain is all reals. Domain of f is all reals. Do you remember that notation of all reals where you just do a big letter R with like 2 bars for the bar? And then the range of f, what types of numbers will come out of that? Will they all be positive? Will they all be negative? Will it be all real numbers? All real. It's a straight line. It's going to have no asymptotes, no holes in it. Range is all real. What about the inverse? If I graph 3 minus x over 4, are there any numbers you can't plug in, that you can't do 3 minus a number and then divide by 4? No, all reals. And the range, still all reals. Things that you would look for domain and range would be restrictions like if something is under a square root, then you don't want to have a negative under a square root. Or if you're dividing by x. Here we're dividing by 4, that's fine. But if you're dividing by x, you can't divide by 0. Or dividing by any quantity with an x in the bottom, whatever would make that quantity equal 0. You can't have that in your domain. All right, so graphically, if you look at the two graphs, they are inverses of each other with respect to the line y equals x. So this dotted line here is the line y equals x. This line here, the black line, is the line 3 minus 4x. It has the y-intercept of 3 and has a slope of negative 4. The inverse is the red line, that's the 3 minus x over 4. It's got a y-intercept of 3/4 and has a slope of negative 1/4. So those two graphs, you see if you fold it on the line y equals x, this part of the graph would line up here, and this red part would line up here. So if you fold on the line, two parts will line up on each other. So that's the symmetry with respect to y equals x. And that happens with every inverse function and its original function. So graphically, if you graph them both and you fold on the line y equals x, you'd be able to tell if they're inverses. So that's graphically how to show that two lines are inverses of each other. And remember that if f contains the point AB, then G contains the point BA. For example, this point 3, 0 here is 0, 3 on the black line. Or the point 1, 1/2 is the point 1/2, 1 on the black line. So the x's and y switch. You can see that graphically too. So does every function have an inverse? Theorem 5.7 says a function can only have an inverse if it's 1-to-1. Now a function doesn't necessarily have to be 1-to-1. A function could have different y values for the same x value, or different x values for the same y value, but not different x values for the same y value. For example, if you have a table, if you repeat the x value, it has to have that particular y value. But you could have a y value that's repeated with two different x values. Do you remember how to test graphically if a function is a function, if a relation is a function? The vertical line test. So if you have a graph like this, it passes the vertical line test. Everywhere you would draw a vertical line, it would go through each vertical line would only hit the graph once, because every x value has a unique y value. But this 5, 6, and 2, 6, that's fine. We can have a graph that goes over to 5, 6, and then another part that goes up to 2, 6. You can have two y values that are the same with different x values. But you cannot have the same x value with, or the two different x values with the same y value. No, that's not what I meant to say. You can't have two different y values with the same x value. So you could not have you can't have a graph that goes to 1, 2, and then 2, 3, but at 2 there's also a 0.7. Because then if you graph that, you graph those 2 points, they will not pass the vertical line test. So that would not be a function. This is not a function. And this is a function. So just telling if something's a function or not is not good enough to determine if it's going to have an inverse. If it's not a function, it definitely does not have an inverse. Only functions have inverses. But it has to be a particular kind of function that has an inverse. A function has to be one-to-one. So that means that for every x value, there's a unique y value. So this 2, 6, and 5, 6 could not happen for it to have an inverse. An inverse, for a function to have an inverse, it has to be one-to-one, which means every x value has a unique y value, every y value has a unique x value. There's no repeats. So 2, 6, 5, 6, you could not have that. And that's easily told by the horizontal line test. If you look at this graph, f of x equals x cubed plus x minus 1, you can see that a horizontal line test, it passes. It also passes the vertical line test. So a graph that's one-to-one has to pass both vertical and horizontal line tests. And then it will have an inverse. This is a function, it passes the vertical line test, but it's not one-to-one because here it crosses 3 times. So that y value is repeated 3 times, so it will not have an inverse function. Another way to tell if a graph is a function that has an inverse is if f is strictly monotonic. And that might be new vocabulary for you. You ever heard of that before? Okay, that's common in calculus, so make sure that you learn that vocabulary. If something's strictly monotonic, it means it's always increasing or always decreasing. If something is strictly monotonic, it means it's one-to-one. So one-to-one is kind of like a layman's term. Like, we kind of understand what that means now because we've used it for a few years. Strictly monotonic is the more appropriate term mathematically to say that a graph is increasing or decreasing all the way on its domain. It's not going to have any up and down turns. So this graph on the left here is strictly monotonic because it's always increasing. And this graph is not because it has some parts that are increasing and some parts that are decreasing. So it increases here, decreases here, increases here. And since we do know calculus, how could we analytically figure out if a graph is always increasing or always decreasing? Take the derivative, and what do you want to know about that derivative? Yep, there can't be maxes or mins. We want to know if the derivative is positive or negative. Yep, good. So let's see if we can figure out if this function is strictly monotonic, because that will tell us if it has an inverse. So on your homework, when it says, is a graph strictly monotonic, you're going to use the derivative to find out. Or if it says, does this graph have an inverse? Does this function have an inverse? You're going to use the derivative to figure that out. So we're going to take the derivative here. This, we're going to have to use a chain rule for. So to take the derivative, we're going to need an inside function is x minus 7, and the outside function is u to the third. What's the derivative of the inside function? 1, and the derivative of the outside function? 3u squared plus 0, and then you multiply the two together. So f prime of x is 1 times 3u squared, replacing u. So the derivative is 3 times the quantity x minus 7 squared. So how can we tell if that's positive or negative, or does it change? If you set it equal to 0, that will tell us if it has a max or a min there. So we can set it equal to 0, and x equals 7 is a critical number. So it's a possible critical number, critical point, those two words are interchangeable. That's a possible max or a min. Then how do we figure out if it is a max or a min? View from chapter 3, huh? Do we want to use, is it an open interval, like intervals, negative infinity to 7, or do we want to check y values? Do we have a closed interval? We don't have endpoints, do we? No, so we got to do open. So negative infinity to 7, and 7 to infinity, and we're going to put them into the first derivative. So what would be a good number here? 0. Put that into your first derivative. 0 minus 7 is negative 7, but then you square it. Positive times 3, positive. So my first derivative is positive there. So what's the function doing between negative infinity and 7? Increasing. If I pick a number like 8, put it in the function. 8 minus 7 is 1. 1 squared is 1. 3 times 1 is 3. So again, I get a positive number, so my function is still increasing. So does the function change directions at 7? No. So 7 is not a max or a min, and my function is strictly monotonic. It's always increasing. So to answer the question, will it have an inverse? Yes. Now that doesn't show you how to find the inverse, it just tells you if it has an inverse. That will be part of your homework. Does f have an inverse? Show it. Show that it has an inverse analytically by taking the derivative and showing that that derivative is always positive or always negative. Well, let's remember how to find an inverse. You've done this before. It's been a couple of years probably. They're on page 346 if you don't remember. But first, determine if it's going to have an inverse before you go through all the work. And we just went through how to determine that. If you can graph it, look to see if it's always increasing or always decreasing. If you can't graph it, then take its derivative and find out if that's always positive or always negative. Second thing, solve the function for x. That's easier said than done sometimes. Interchange your x and your y. And then you will be solving for, nope, we don't have to solve for that because we solved for x in the beginning. There are two ways to do it. I don't know which way you learned in pre-calc or algebra 2. You can interchange x and y first and then solve for y, or you can solve for x and then interchange x and y. Either way, those two steps are kind of interchangeable depending on which way you like to do it. And then define the domain of the inverse as the range of f of x. Verify that the inverse of f put into the f function equals x, and the f of x put into the inverse equals x. So after step 3, you found the inverse. Steps 4 and 5 are extra things that the book might ask you to do, or a test might ask you to do. So let's find the inverse of f of x equals x cubed plus 1. Okay, so to find the inverse of f of x equals x cubed plus 1, first, this is the letter y, so where it says interchange x and y, that's my y right there. So first I'm going to solve for x. So I'm going to subtract 1, and then take the cubed root. So x equals the cubed root of y minus 1, and then I'm going to interchange my x and my y. So the cubed root of x minus 1 equals y. Okay, so let's graph them now. So the original function was x to the third plus 1. And the inverse is the cubed root. Oops, I didn't want that. The cubed root of x minus 1. And what should I notice when I graph them?
They should be, what's it, they should be like that. Yeah, reflected.
Reflected over what?
Y equals x.
Y equals x, so I wonder if it'll let me draw in here. No, it doesn't let me draw in here, but that line right there is where they should be reflected over, and they are. So, Any questions about how to find an inverse? Nope, okay. There's your homework.